Yeah. Are you able to hear me now? Yeah. So far we've been talking about linear data structures, right? Arrays, queues, stacks, linked lists. Starting today, we will basically be talking about nonlinear data structures. We have a series of lectures wherein we will discuss three most common nonlinear data structures: heaps, hash tables, and binary search trees. So I'll just tell you the agenda for today. So uh, today we will basically be looking at, obviously, as I told you, we are talking about nonlinear search structures. I will explain in a moment what that means, what this jargon actually means. And in that today we will be looking at unordered search structures. And in particular, we'll be looking at hash tables and what is their USP, what kind of applications can be solved using hash tables. So this will be a major portion of the class will be devoted to learning this. So how many of you are familiar with hash tables? Like, what is the level of familiarity? Do you understand the implementation of hash table, or would you like me to talk about the implementation as well, or just the applications? How many of you want me to talk about the implementation as well? Not familiar, not familiar, not familiar, not at all. Yeah, Karan, I understand. Karan might be having probably one of the most toughest times because you're from first year, you have no background at all. We'll come to USB. Don't worry. I will explain everything. I've just summarized. Not familiar. Okay, cool, 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 cool. Should be fine. Then we will start right from the basics. Uh, Anyone who is familiar with the theory of hashing? No, right? You can speak up right now. Now is your time. Otherwise, we will start. Okay. So basically, computer science is all about data, right? So you have what were so one of the most fundamental problems that computers solve is they operate on data, right? Data of all kinds, all types of data, and computers basically work with data. And with data, basically, um, if you look at data, fundamentally, there are three types of tasks that we need to do on a daily basis. So there is data which keeps coming in at regular intervals. You need to insert data, you need to delete data, and you need to search for data items. So just to give you an example, let's say you are talking about Amazon. So Amazon has this entire database of items, right? That it wants to sell, or the items that it displays when you log into Amazon and when you are browsing through the categories, right? So these items are nothing but data points. And what does Amazon do? Amazon stores this data, correct? And when you search on Amazon through some keyword, it retrieves data items that match that criteria that you have specified in the search category, right? When you click on an item, it double clicks on it and gives you more information about the data. Then when a new seller lists an item on Amazon, it has to insert that data in its database, right? When a item has already been sold, it has to remove that item from the database. So typically any computer or any software that you build these days will work with data, and you need efficient ways of doing these things on the data. This is basically the problem. Correct? Everyone understands the problem, or should I go into more depth with respect to the problem? So just two lines, I told you that it is all about data. Computers work with data, and softwares work with data rather. And we want efficient, so data keeps coming in and keeps going out. So you need to have some place where you store that data, right? And you need to, when the data comes in, you need to insert that data item that comes in into the data, into the place where you have stored all the data. Then when the data is, there will be a time when the data will need to be removed from the place where you have stored it, right? And then there will be users who want to access a specific data item. So you will want to search for that particular data item from in the place where you have kept it. Correct? So this is the problem, that this is majority of computer science. That's it. This is the biggest problem that computer scientists have been solving for some time now. And now if this is the problem, then basically comes data structures to the rescue. So what are data structures? So then scientists told us, people who do research all the time, they told us that you want some place where you can keep the data, insert the data, remove the data, and as well as search for that particular data item. So scientists said that why this place where you keep it, you will need to organize it in a certain manner, right? This needs to have a certain structure. And that's why this place that where these data items are kept is called nothing but a data structure. So think about data structures as an analogy to your cupboard or a wardrobe. So if you have a wardrobe in your house, you will recall, or just imagine you have racks, right, where you place clothes, and you place different items in different racks. You organize so here your data is your clothes that you are putting, and the data structure, the container where you are putting it and organizing it, is the wardrobe. So how do you organize it? You stack up items one on top of the other. You have a section for jeans where you put all the jeans. Then you have a section for t-shirts where you put all the t-shirts, right? So why does that organization help? So that in future, tomorrow, if you want to take a bath, assuming you take a bath, you want to wear a t-shirt. So it's easy to retrieve that t-shirt from that. You know that it's that section of the wardrobe where the t-shirt will be stored. So you can retrieve it efficiently. Similarly, once a particular shirt or a jeans has been washed and you want to put it in the cupboard, you know that you will not take a lot of time to put it in the cupboard because it has been organized in a specific manner. You know that it's the third rack which contains the jeans. So you will straight away go to the third rack, and you know that you have stacked up jeans on top of the other. So you will put the jeans just on top of whatever the rack has already been created, or whatever the pile has already been built, right? So what have you done? You have organized your data, which is your clothes, in a specific manner in a container, so that you are able to insert, delete, and search efficiently. You don't spend a lot of time. Compare this to a scenario wherein your wardrobe did not have any organization. You were, as in when you were getting clothes, you were just dumping it into the wardrobe without any particular structure or organization. In that case, searching would have been very messy, right? You would have to literally remove every item from the and check whether it's the cloth that you are looking for. And if it is not, then you would have to put it back and then look for the next item. It would have been very messy and very time consuming. Similarly, when you are removing a cloth, it would have been very time consuming to remove a cloth. You would have to literally look for that cloth from across the entire spectrum of clothes that you purchase. And if you are a girl, then that problem is even bigger, I'm assuming. No stereotypes. So basically what you have done here is you have organized the data in a manner so that you are able to do these operations efficiently. So your wardrobe here is a data structure where you have organized the data, which is your clothes. Similarly, in computer science, you have data which you store in data structures in the memory. So these data structures are stored in the memory, right? So this is how scientists said that we will tackle this problem that we are faced with. And so then there began a whole lot of research on these data structures. What kind of organization can you do to be able to solve special types of tasks. Let's say you want to search efficiently, then you can organize the data items in a specific manner so that you are able to search faster, right? And in that, amidst all this, basically people devised arrays. And what did people say? People or the scientists said that there could be one possibility wherein you store data items one after the other in a contiguous fashion. So store data items one after the other, I1 in the first cell, I2 in the second cell, I3 in the third cell. Store them one after the other in a contiguous fashion. So what is the benefit of this? The benefit of this is that if you want to retrieve an item IN, you know that if you know the starting address, the place where you kept I1, you know that from that address, if I just go n steps, I will be able to get IN. So this is basically, I could just get an item IN in order 1, or basically very literally without any time. I can straight away from here jump to this and retrieve that item. Correct? So that was the benefit that arrays offered. And this was the USP, that you store data items in a contiguous fashion. We will come to what USP is, don't worry about it. But so this is basically one. But then people said, okay, this is fine. But the problem with this is that if you want to insert randomly at a particular location, you will not be able to do that efficiently, right? So you will need to shift items here. Then only you can insert it at a particular location. So then scientists said that, okay, then let's remove this contiguous property and let's link data items one after the other. And that's how basically linked lists were born. And people said that if you link data items one after the other, then it's very easy to insert at a random place. You just need to link the previous item to this item and this item to the next item which was there previously. And if you do that, then you will be able to insert very fast, right? But so that's how linked lists were born. Similarly, people came up with other data structures to solve specific types of problems. So is this introduction to the motivation why we are doing this? What is the problem that we are solving? And what data structures are, what kinds of data structures we have already looked at? Is this clear?
Yes, sir.
Yeah, any questions? Speak up if you have any questions. Okay. So if this is clear, then let's come back to the problem. What was the problem? The problem was we had data items that are coming in. We need a way to efficiently insert, delete, and search. This was the problem statement. Now let's debate on what will be the time complexities, or what will be the amount of time it will take if I use the data structures that I already know. Okay, so let's talk about a sorted array. So a sorted array is an array wherein you are putting data items in a sorted fashion. And let's say this is an array where you already have items which are in a sorted fashion. Now you have another item ij which is coming in. So if you want to insert in this sorted array, how much time will it take to insert? If the size of this array is n, can you unmute and speak? Do you understand the problem, others? So now basically with the motivation, and we are basically just looking at the existing data structures that we already know, and we are brainstorming on what will be the complexities if we do these operations in the existing data structures that we know. So for that, to that effect, I told you that let's talk about a sorted array first, and what will be the complexity if I insert a data item in a sorted array. So what will be the complexity?
Overfan.
O of n, right? Others, do you follow? You are able to see this, right? Just stop me if you don't. And please unmute and speak. So why will it be O of n? Because you will have to find the appropriate place to insert this, right? So if it is 5 and you have 1, 2, 3, 7, 9, 10, then you will have to find 5 here. So this finding will take log n, right? You can find that item place where you have to insert in log n using binary search. But after that, when you are inserting it here, how will you insert it? You will have to shift these elements to the right, correct? So you will have to shift 7 here, 9 here, 10 here, and then insert 5 here. So that shifting, if you have to insert an element at the beginning, will take n time. So the total time will be order of log n plus n, right? Which is order of n. Log n is for searching, basically searching for the position where you have to insert it. And n is for inserting, the actual act of insertion. Right? Similarly, if you have to delete a data item from a sorted array, how much time will it take?
O of n, same.
Same. How? Why?
After deleting, we need to shift the elements to.
Yeah, so the same logic basically. Once you find an item that you want to delete, finding can take log n. You can find, because it's a binary, because it's a sorted array, you can find using binary search. So finding will take log n, but after you have found it, you have to remove it. So how do you remove it? You have to shift the other elements one place before, which might potentially take order n again. And what about searching a random element?
Log n already binary search.
Log n, right? So binary search you can do too. And what about searching for the minimum?
O of 1.
O of 1. Correct? So this is the complexity if you go ahead with a sorted array. Now let's talk about unsorted array. So what will be the complexity of insertion in an unsorted array?
O of n.
O of n. Why?
It's actually O of 2n, right?
You can just, if it's an unsorted array, you can just insert at the back, right?
But
Which is order 1.
yes, yes. I thought in specific position.
No, unsorted array. So you have to just insert that data item. It's not never at a position. That position is basically the underlying structure of the array, like the data structure that you are keeping. What about delete?
Deleting a specific element or the first element?
Deleting is a
Think O of
specific,
n.
any random element that is given to you.
O of n.
O of n.
O of n it will take, right? Because you will have to search for that element. Searching itself will take O of n. And after you search it, you will have to shift elements. So you will take order n. What about searching for a random element? This will be order n again, because you will have to do a linear search on the array. And what about searching for the minimum?
O of n.
O of n again, because the array is not structured in any fashion, right? So this is for the unsorted array. Now let's talk about a sorted linked list. What will be the complexity of insertion in a sorted linked list?
O of n.
Sorted linked list. Will it be of 1?
It would be O of n because we need to find the position of the.
Yes,
So
you
it-
need to find the position where you have to insert it, right? Because it's a sorted linked list. You cannot just insert it anywhere randomly. Correct? So that finding, so let's say you have 2, 3, 5, 7, and you want to insert 4, you will have to find the position that 4 is here. So for that, you will have to traverse from the beginning till you reach a point where till you reach 3, and then you insert after 3. Right? So this searching will take order n, and then the insertion is order 1. So the total time in a sorted linked list is also order n for insertion. What about deletion? It's the same. If you want to delete a random element, you will have to first search and then remove. So searching is order n, but the actual act of removal is again order 1 because you just have to change the pointers. So deletion is also order n. What about searching for a random element? This is also order n. You cannot do binary search here, right? Because it's a linked list. Do you understand why you cannot do binary search on a linked list? Can you tell me why?
Because elements are not stored linear in memory.
Yeah, I mean you don't know how to access the middle element in order one time, right? So what do you do in binary search? You access the the middle element. You cannot directly go to mid. Yes, Karan, you're right. In arrays, the benefit was that you had random access. So because you had random access, you straight away knew that a of mid will go to the middle. So you cannot directly go to the middle. You have to do a linear pass to reach the middle, n by 2. So that takes order n to reach, and then you can maybe divide it into 2 halves and sort these individually, like a search basically, depending on whether it was greater than mid or less than mid, whatever the theory is for binary search, right? So you cannot do binary search. So the searching, even if it is a sorted list, will take order n. And what about searching for the minimum?
Of 1.
This will be O of 1, right? Because the first element in the linked list will be the minimum. So now, similarly, you can extend this for unsorted linked lists. Let's quickly finish it. So in unsorted linked lists, what will be the time complexity for searching? First, let's talk about insertion. It will be order 1, right? You can just insert at the back because the linked list is unsorted, right? When you are deleting, you will have to again search for that item. Searching will take order n, and then the actual act of deletion will take order 1. So the total time will be order n. If you have to search an element, you will again have to traverse the entire list. So it can take up to n time. If you have to search minimum in an unsorted list, it will take again order n time because you will have to traverse the entire list, right? So I just gave you a heads up on if we go ahead and use the data structures that we already know, what will be the time complexity or how much time we will take for each of these operations. So I just took the case of a sorted array, unsorted array, sorted list, and unsorted list, and told you this. Is this complexity analysis for all the 4 clear? Can I have a set of acknowledgements before I proceed?
Yes,
Any questions on this? If you have people who have no background, is this clear? People who knew, is it right?
sir. Excuse me.
Mm-hmm.
I have a doubt. I mean, how to insert element in the sorted array?
How to insert element in a sorted array. So let's take an example. If you have 2, 3, 5, 7, 10, let's say you want to insert 6. So what you do is first you do binary search to find 6. This part is fine, right? You can do binary search to find 6. Find 6 as in find the smallest element which is greater equal 6. Right? That we have done in the class also.
Yes, sir.
That should be fine, right? With that, you can find that you have to basically insert it here. After that, what you will do is you will basically keep shifting elements to the right. So you will put 7 here. You will put 10 here. You will keep doing this till you reach the end of the array from here, and then you will put 6 here. It is similar to insertion sort, if you know the code for insertion sort, right?
Sir, I mean, the
So
size of the array is a fixer Sir, how you increase the size?
So size can be typically, what you can do is you can keep a, yeah, pushback is fine. Let's not talk about the implementation, but size, what you can do is you can typically in have a big array to begin with. A fixed size, if you're going with a fixed size, you, let's say you have an array of, you have done some estimates, and based on that you have arrived at this number that I will not have more than 10,000 data items in my array at any point. So you straight away reserve memory for those 10,000 data items. That's one way you could do it. And then as and when elements are coming in, you are basically, your size is, you are getting elements. So once 2 comes in, you will put 2 here, but your array has already, like, you have already allocated memory for these 10,000 data items. And once you are about to exhaust these 10,000 data items, what you can do is you can resize this array. So resizing this array will again take time. You can allocate another array of 20,000, let's say, if you want to double it, and you can copy that 10,000 here. But this is once in a while, right? Once in every, after every 10,000 operations, you might have to resize. So it's not, it is something that can be done offline, and it is not a bottleneck here, but you can reserve memory for that beforehand, right? So that's how you can basically do it. And that's how basically it is done in the, in STL also. In vectors, in C++, what they do is, when you do a v dot pushback, what it does is it inserts one element, but it allocates memory twice the memory of whatever is the current size. So it keeps another, so if the total size of the array so far is X, when you insert one element or push back one, what it does is it allocates another X to this array. So it does that. And then when you are filling it, it's fine. But when it is about to reach the capacity, it will again allocate more memory for this. Allocate more memory as in, it will allocate another array with bigger size and copy the data items. Clear?
Yes,
Did I
sir.
answer your question?
Yes, sir.
Yeah. Karan, is this fine? Do you understand this? Yeah. So any more questions in this? Okay. So now let's move on. Now you see that with whatever, so the basic underlying fact is that with the data structures that we know as of now, you if you see the, in the linked list, if we add at the end, it will be O of n. That's not necessarily true. You can keep a pointer to the head and the tail at all times in the linked list. So when you are inserting, it will be an order 1 operation. Those are small tweaks that you can do, right? And in fact, again, here the list class of C++ STL also keeps a pointer to the head and the tail. So whenever you do a pop back to the list, it is an order 1 in order 1. Whenever you do a push back to the list, it is an order 1 operation, even for a list. And if you do a push front to a list, that is also an order 1 operation, because it maintains pointers to the head as well as the tail of the list. So the beginning is the head, right? Sir hai ye iska. And this is the tail. So you can do that. Okay, any more questions? Okay, so if that is fine, so with all the data structures that we know as of now, I mean, you can, so your homework is just do the same analysis that I did for stacks and queues. Now you know what stacks and queues are, right? And you know the complexities. Just do the same analysis of insert, delete, search, insert, delete, search for stacks and queues, and tell me how much time will it take for each of these operations. So this is the homework that you should do. We can discuss it tomorrow. I did it for sorted arrays, both types, sorted and unsorted, and I did it for lists. sorted and unsorted. So try it for stacks and queues. Those are like the 4 data structures that you know or you have read so far. So the bottom line is, okay, I will get back to that. Basically, I will talk to Sudhanshu and ask him like where are we with respect to stacks and queues. I think he did say that. Okay, yeah, okay. So the bottom line of behind all this is that even if we use these data structures, at least one of the 3 operations or at least 2 of the 3 operations is order n, and this is very inefficient. We cannot afford order n time for these operations simply because these operations are very frequent in today's world. There are two reasons. These are very frequent in today's world, and we work with large volumes of data. So because we work with large volumes of data and these operations are very frequent, we cannot even afford to have a linear complexity for each of these operations. So we cannot, typically these insertions need to be done in microseconds or milliseconds. You cannot even afford to spend 1 second on this. And if you know that if you have, you can do at most 10 to the power 7 operations in 1 second. So if you have a data structure of 10 to the power 7 size, let's say it's an integer. So 10 to the power 7 into 4 bytes. This is all. If your data structure exceeds this size, then your insertion, deletion or searching will take more than 1 second. And you cannot afford that in today's world simply because there is the frequency at which these requests come is very, very like large, and the volumes that we work with, this quantity is very meager compared to the volumes that we work with in today's world. We work with terabytes and petabytes of data, not even gigabytes. This is not even, this is 40 megabytes, right? This is not nowhere close to the to the volume that we work with. So with 40 megabytes of, as soon as you have 40 megabytes of integer data, just think about it. You will start taking more than 1 second to insert. This is really a bottleneck. You cannot afford to have that. So the bottom line is we need efficient structures, more efficient structures for these. Okay. So far, so good. Can I have acknowledgements so that I know that you are awake, alive, awake, not slept, following things? Yeah. So now let's think about the ways we could do it. One way we could do it is by having a direct access table. What does that mean? That means that let's say you want to store integer data. So let's say you want to store numbers 2, 3, 5, 7, 10. One way you could do that is that you first of all decide on the range. So on the maximum value that can occur. Let's say you know this already, that the maximum value that can occur, it cannot occur, any item that I get will never exceed, let's say 1 million. 1 million is 10 to the power 6. So now, if you know that, then one very simple way you could design a data structure is that you can have an array of size 10 to the power 6. Right? Or 10 to the power 6 plus 1 if you are doing zero indexing. And then when you get a data item, what you can do is you can go to that corresponding index and store it there. So 10 you will store at index 10. 7 you will store at index 7. So what is the benefit of keeping this? Now, if you want to insert a data item, how much time is it taking?
O of 1.
O of 1, right? Everyone is clear with this? It is simply that you simply go to that index and you put it there. So retrieving that index using the property of the arrays that you can randomly access any item in the array, it will take order 1, right? Similarly, if you have to delete a data item, how much time will it take? You can simply unmark it, right? You can replace this with, let's say, -1, a value which is not in the range that you are considering. So you have a way of knowing that there is this data item does not exist. So then deletion becomes order 1. Correct? What about searching? Searching is also order 1. You can simply go to that index and see if it is -1, then you know that that element does not exist. And if it is some other value, or if it is equal to the value, then you know that that element exists and you can return true. Right? So you can have something like this, which gives you constant time operations for all these. Similarly, searching the minimum is also order 1 here. You just have to look searching. What is the complexity of searching the minimum here? Is it order 1? What is the searching? How much
Order
time will
n.
it take?
Order n.
And can you do better?
A log n binary search.
Yeah, you can do binary search, right? So how can you do binary search? You cannot do binary search. What will you search for? You want the minimum, right? So basically you have to find the first index which is not -1 from here, starting from the beginning. So can you do that using binary search? You cannot, because you will have -1 at several other random places also, right? And you will have values potentially. So the question is that you have to find the first non -1 position. So think about it, whether you can do binary search or not. I mean, the first thought that comes to my mind, I don't think you can, but it might be possible. So searching minimum is order n or log n. We will see. You have to tell me which one is correct, whether this is correct or this is correct. Okay. So this is basically a direct access table. If you were to use something like this kind of a data structure, then you get these operations in order 1 time. But what is the flip side of this, or what is the downside of using something like a direct access table? Did you understand what direct access tables were? What did we do with that? Wastage of memory. Okay. By fixed size, you mean it cannot handle dynamic range, right? Yeah. So one of the very obvious downsides is that if your data items are sparse, let's say you have 2, 3, then you have 1,000, then you have 1,100, then you have 5, then you have, uh, let's say this is 5,000, then you have 5,200. So if your data items are very sparse, then most of these cells will be empty or -1. Only some of them will be filled. But what you have done is you have allocated a huge amount of memory to store these 6 data items. Yeah, right? So you can always bias this. You can have 5 data items, and the minimum of that is 2, and the maximum is, let's say, 10 million. So just these 5 data items you can have, and in between, let's say 2, 3, 7, 500 and 10 million. Let's say these are the data items. So for just these 5 data items, for which if you had used an array, you would have used up 20 bytes of memory. Here, how much you will be basically be using 10 million into 4 bytes of memory unnecessarily. Most of the cells will remain empty. So that's basically a downside of this. The other downside is that if the range is too big, then you cannot allocate contiguous size memory or array for that of that size. So typically you can allocate arrays of 10 to the power 6 in the stack, or 10 to the power 5, even like sometimes it complains for 10 to the power 6 also. If you go ahead and allocate arrays of larger size, then it will not be possible, because the memory is limited, the stack size is limited. So you cannot handle data items which have ranges beyond what your compiler can support. The other thing is, here you are, so that's the second downside. The third downside is that you are fixing the range. So you are saying I can only accommodate data items between 2 and 5200. I cannot take any data item which is beyond 5200. So tomorrow, let's say your requirements change and you have a data item which is, let's say, 10 lakhs. This is one number that you want to insert. You will not be able to insert. You will have to create another direct access table of size 10 lakhs plus 1, and then transfer all the data items from this previous access table to this, and then insert this new element. So this is not a very feasible way of doing things, right? So these downsides are clear to everyone. Yeah, I will start taking names now. Saurabh, Ayush, how are you? Long time no talk. Abhishek, is this clear? Anushka, Divya, long time. These are all people from previous batches. Hemant, how are you? Mantavya, long time no talk. Shravan as well. Samarth. Yeah, I guess Tanya is not here. Okay. But we still have a lot of people. So those are the downsides. So then people said, now think about what is the problem here. The problem here is the large table, right? This is the problem. Just think about the problem. This is the large table is the problem. And what is the benefit here? The benefit is the direct access that you are getting. Right? So you are basically getting to find the location where that element is through indexing, right? You are getting a direct access to that through indexing. That is the benefit that this data structure has provided, but in its raw form, it is not suitable for consumption because of this downside that was there. So people said, now think about the most obvious way of getting around this problem. People said, why not you create a table of some fixed size, which is not dependent on the range of data items that is coming in. So now you create if your computer can support 10 to the power 5 data items, then you create an array of size 10 to the power 5 only. But now what you do is, whenever you have data items that are coming in, you map them to a value within this range, 0 to 10 to the power 5. So whatever data number comes in, 3 comes in, you map it to some index here, and then you put it there. 10 to the power 7 comes in, you map it to some location in the range 0 to 10 to the power 5, and you put it there. So if you can have some kind of this mapping, then you can still leverage the benefit of this indexing or this direct access. Right? Do you follow this mapping part? Is it making sense? Like the most obvious, think about the most obvious way of alleviating this problem or getting around this problem. This is how they would have gotten around this problem, right? Keep a mapping. The problem is that your data set is large, right? So keep a mapping. Keep a function, more precisely or more mathematically, keep a function which maps. So the function's domain, the function's range is what is the its domain, right? The function's range is basically domain is the domain is basically the range of the numbers that you are getting in, and the range is 0 to 10 to the power 5. So keep a mapping of that type, and then you will be able to do that. And now you will still have the same benefits. If you want to, how will insertion look like? If you want to insert 10 to the power 7, you will use that function. You will get the value of f 10 to the power 7, and you are guaranteed that this will be in the range 0 to 10 to the power 5. So now you can do a of f 10 to the power 7 to randomly index into that, and you can check if it is -1 or not. If it is not -1, then you can say that it exists. So searching is still order 1 if this function through which you are computing is order 1, right? Similarly, if you want to insert a data item, let's say you want to insert 10 to the power 9, you can insert it. You can get the index from f 10 to the power 9. This will give you an index between 0 to 10 to the power 5 where you have to insert it, and then you can simply insert it. Right? Deletion also, you can simply go to that data item and you can mark it as -1 or whatever dummy pointer indicator that you are using to represent it as, and correct. So it is still order 1, provided this function that you have, you are able to compute this in constant time. Clear? Is this clear? Why these operations still remain order 1?
So the maximum range of the indexes is up to 10 to the power 5 or 6, right? And the maximum size of the element which we can fill up is up to like 10 to the power 9 or even more than that.
Yes. So we will come to the problem that this will have. That's basically the next step. But assuming you have this ideal world wherein you have this kind of a function, do you understand that all these can be still done in order 1?
Yes, sir.
Yeah, we will come to problems. Okay, so if this is clear, now let's double click on this f, this function that I'm talking about. So this function takes a range which is very large. Let's say your data was actually in the range 0 to 10 to the power 20. So this function takes elements from this range and maps it to a smaller range. Let's say 0 to 10 to the power 6. Correct? So naturally you will have the same different numbers here will map to the same location. That's very natural, right? Because this is bigger compared to this. So naturally you will have two numbers x1 and x2 such that f of x1 will be equal to f of x2. Right? Because the input domain is very large and the range is smaller than the domain. That's why you will have this. And this is what we call collision. What has happened here? You have two data items which are mapping to the same location in the table that you are creating. Right? So how can you take care of this now? This will happen. No matter how good an F you choose, this will happen simply because the range of input is much greater than the range of output, or the domain is greater than the range. So how can you take care of this? Now let's think about ideas. How to take care of this? Is collision clear first of all? So now tell me, how can we take care of this? Like, what is the most naive way you can think about how you can take care of this?
Each index could be an array itself, and we can store.
Yes. So what you could do is each index could be, so each index, this, let's say this is f of x1, the location, and this is f of x2 also. So each index could be a data structure in itself. You could keep this as an array or a linked list, right? Wherein you can store x1 and x2 both. And potentially if you get another x3 in the future, which is also for which the computation of f yields the same value as it had yielded for x1 or x2, you can put that also here, right? And you can keep doing this now for every x. Correct? This is one way you could go about solving this problem. And this way of solving this problem is called chaining. So what have you done? You said, I will just summarize what we have done. We started with the motivation that we want to search, insert, delete efficiently. We said that the existing data structures are inefficient. We are not able to solve the problem with them. We need better data structures. Somebody told me that let's use direct access tables, but we said that the problem with that is that the range could be very large. So this unnecessary is the wastage of memory. So then the most natural next thought was that why not keep a mapping? So this mapping or this function that we keep is called a hash function. And we said that why not keep a function which maps elements, and then you can use that mapping to insert elements in the table now. And then we said that, okay, but the problem with that is that there might be collisions. Why will there be collisions? Simply because the input space is much larger compared to the output space. So we said we could have collisions. And we said that one way you could resolve these collisions is by chaining. This is all that we have done in this 1 hour or whatever time we have spent. 1.5 hours, 1 hour actually. I will take a moment, a pause, and you can ask me questions on whatever we have done so far. If anything is not clear or you want me to repeat, if you have any follow-up questions on anything.
Sir, am I audible?
Yes, you are.
In chaining, you say the hash function gives the same location to both elements.
Right.
But when we store it in the linked list, how do we know the exact position of the linked list, like the first element of the linked list, the second?
Yes, so that will not be now with chaining. If you are searching for x1, it will not be constant time. It will be basically order of the size of that chain. You will have to still traverse through that chain. So from x1, you get f of x1 where you enter. Now here you have a chain, right? It can be a linked list, it can be an array, it does not matter. But once you have a chain, you will have to sequentially traverse through it to find x1. So the total complexity for searching an element is no longer order 1 now. It is basically order the size of chain of x1. Right? So that is the trade-off. This is the time that we are now spending. Similarly, now let's talk about insertion. If you want to insert a data item x4, how will you insert it? You can simply get f of x4 and then you can append, let's say this was f of x4. Then what you can do is, let's say it already has some chain. It will have some chain, right? You can simply insert at the back. So this insertion might still be order 1. If you keep a pointer to the tail, or if you have an array, you can just push back. What about deletion? If you want to delete an item, then you can, let's say I, so you can take f of I. Now you know the position where you have to go. Here you will again have to delete as if you were deleting in an array or in a linked list. So it could again take the time, which is order size of the chain of I. Similarly, searching now, if you want to search for a data item, this is the amount of time you will take. Once you reach that index, you will have to manually go through each of the data items. But this is basically the time complexity for inserting, deleting, and searching. And if you basically, if you have a function, hash function, which is well behaved, what that means is that if well behaved, as in if that hash function, this is the input space and this is the output space, right? If that hash function is able to uniformly distribute these data items, what does that mean? That means that on average, each of these slots have fixed number of items. So it is not disproportionate distribution. It is a uniform distribution if your hash function is able to do such that, let's say you're talking about a particular cell, then this cell has some key elements. All the cells have key elements. So it has been able to divide this entire output space into equal chunks for each of the indices. If it is able to do something like that, if you are able to come up with a mapping, that will solely depend on the f, right? So if your hash function is well behaved, what it means by well behaved is this criteria. If it is able to do that, then on average, you will be spending very less amount of time in searching or in inserting or in traversing through this list, right? But if your hash function is not well behaved and it happens to map everything, let's say the worst case, everything to the same location, then then basically you have not solved any problem. Now if you want to search an item, you will still take order n, where n is the size of the input, correct? So those are basically the two ends of the spectrum of f. The best hash function is one which can give you uniform distribution. In that case, almost every retrieval will be constant time. Why will it be constant time? Because typically, if your total size is n and the size of the table is k, n by k elements are in each of these slots. And you have some theory wherein you can prove that this is constant. If k is of the size of order n, then this is basically constant. So it takes constant amount of time to search. This is the best case scenario. And the worst case scenario is that it maps everything to the same location. Then you will take order n time. So it all depends on the hash function, how well you are able to insert, delete, and search. Now I will take a pause and I can take questions.
Sir, was that like kind of a, let's say, the internal data structure of the unordered maps? Because in the ordered maps, we can store infinite, like different values having the same indexes, or that it follows the chain.
I have not introduced ordered maps and unordered maps yet. So like for others, it might be confusing, but I can answer your question. What is your question on ordered maps?
So like the thing which I explained about chaining, like for one particular index which we are getting access through and we are storing like
ordered
multiple
maps
values.
are implemented using binary search trees, and unordered maps are implemented using hash tables in C++. If that answers your question, I think that will answer your question.
Okay, sir.
I mean, you can ask if you don't understand. It's perfectly fine. So we will come to that. We will gradually build up to that as well. Are we also creating frequency array in that direct access table? What do you mean, Karan? Can you unmute and ask?
Sir, for multiple, if there are repetition of data,
yeah, you can increase the count. Maybe that's one way you could do it. If you have the same element coming again and again, you can keep incrementing the count, because the number you already know, right? That it is the number is the same as the index. If you have that, yeah. If you know that repetitions are not allowed, then you can either keep one or you can keep that same data item. Can you explain the difference between direct access table and hashing? So direct access tables are one particular type of hash tables where you store element where the mapping is one to one. Did that answer your question? So basically, that's a good question. Let's discuss this. So I just told you two data structures, right? I told you a direct access table, and then I told you another table, which I will now name it. If for people who don't know, these tables are called hash tables. The table that I told, wherein you have a function and you map it and then you insert in the table. So those are called hash tables. So Sai has a question that can you explain the difference between this and this? Can you tell me what is the difference? So direct access tables are basically a subset of hash tables. So they are a specific type of hash tables wherein F is one to one, right? It's a one to one mapping, and it's actually one to one and identity mapping. Do you understand this one to one identity? Identity is F of X is X. So if your function, just think about direct access table, they are basically nothing but you are mapping the same, the F of X to X only, right? You are mapping X to X, the same element to the same location. So basically, if so your mapping function is an identity function. So basically direct access tables are a specific type of hash tables wherein the mapping is this identity function. Any more questions? You will have questions, please ask.
How to decide the function?
How to decide the function? That's a good question. So there has been a lot of research on how can you how to go about choosing a hash function which gives you this well-behavedness, well-behaved property that we are talking about. And there has been research by mathematicians. They have so see, when you want to contain the entire output to a specific range of input, you could do modulo, right? That's the most obvious thing that comes to your mind. Just do a modulo n where n is this size. So this will basically always restrict it to 0 to n minus 1, right? So there has been theories around what is the n that you should choose so that you are able to distribute this uniformly, and people have come up with proving facts that if you choose n as a large prime, then basically you will have this well-behavedness. Then so that is one thing. The other thing is different data types, they have different different heuristics around how to go about finding a function. Strings, if you have, one way you could do it is you could simply sum up the ASCII values of each of them. So that way you will have an integer now, right? ASCII value of A is, let's say, 96 or 65, whatever it is, 97. And you can just sum up ASCII values and then take a modulo n. That will basically give you a number in this range, right? So there has been more research around should you go about just summing the ASCII values, or should you just take a prefix of that and just sum the ASCII values of that. There has been research on how to find the size. So modulo, the thing that you take modulo with, and typically you take large prime numbers as those. They have proved that if you take these as large prime numbers, then your function will typically distribute uniformly, because that is the property of prime numbers. Like there are rigorous mathematical proofs for that. Let's not go into that. If you want that discussion, I can forward you some theory on that. You will it's mathematical, it's highly mathematical. So for our practical purposes, basically we get functions. People have, so this is like this field is like the compiler's field. There has been enough research on this. it has become a commodity and you can just buy it. Just like compilers, you just buy a compiler and use it, right? People have already done enough research on it and you have a compiler which you can use as when you want. Similarly, hash functions have people have done enough research and you can just buy a hash function and use it, and they guarantee that they guarantee like with 99% confidence that this will be the case. So if you really want to get into the specifics of the hash function, let's take it up offline, or maybe I can share some reading materials also. Okay, Vidyut, is that fine?
Yes, sir.
Yeah, but I just gave you a heads up on how they go about designing the hash function, right? So this should give you enough feeling on how they go about designing hash functions. More questions? Ask me. I know there will be questions. Feel free to ask any question, any kind of question. Collision chaining. If there are no questions, can I get a final set of acknowledgements before we move on to direct addressing, open addressing? Where are you guys? Are you dead? Others? Should I start taking names? Dominic, how are you? Both the Pranavs. Are you guys good? Sakshi, it's been a long time. We talked. How are you? Shubham, Susrit as well. Yadu Krishna, how are you, man? It's been all good. Okay. So this is one way you could do it. Now let's talk about another way you could basically do the same thing. So this is one way. Now, so this is called chaining. I just told you one way you could go about doing the entire story that I told you. There is another way you could go about doing it, which is called open addressing. So basically what they say is, again, that when you want to create a table, create the table of that whatever size you want, n. And that n could be much small compared to the range of input that you are getting. So create a table of size n. When you get a data item x, you find the position where you want to insert it in the array by getting fx. So f of x will give you the position where you want to insert it. So find that position. Now, once you have that position where you want to insert this x, you insert it if there is no other element present here. If there is an element present here, what you do is you just keep going upwards till you reach till you find an empty slot. If there have been elements which have already been put here, then you keep going up till you find an empty slot, and there you can put x. So basically here, the total amount of space that is taken is n only. So they are trying to fit everything in n. In chaining, what we were doing was that apart from this n, we needed additional space to store the individual elements when we were chaining. Here we are storing it in the table itself, but it might be the case that we are storing it in a different location. So you basically keep, so this is called probing. You keep, what is probing? Probing is basically you keep looking for an item, looking for a place. So for x, you keep looking for a place where you can insert x. So you are probing this for and checking whether it is the place where you could. Then you are probing this and checking, can I insert it here? Then you are probing this and saying, oh, can I insert it here? finally you probe this index and you saw that, okay, I can put it here because there hasn't been any element which has been put so far. So let me put it here. So this kind of this mechanism is called probing. And why is this technique called open addressing? Because for X, you don't have a fixed address, right? This address is open, and this address typically depends on the picture of the table at any point in time. It might happen that the address of X is f of X itself, or it might happen that the address of X is f of X plus 5 or minus 5. So the address of every element is open. That's why it is called an open addressing. Things will become clearer. Let's take a very small example to understand this. Let's say you have a table of size 10. So you have slots for 0, 1, 2, 8, 9, and let's say your fx is nothing but x modulo 10. Very simple function. It just takes any random number and restricts it to 0 to 9 through the modulo function. Okay. And now let's say you have numbers which are coming in. Let's say you have 3, you have 5. Let's just insert some small numbers, 7. Now let's insert 15. Let's insert 6. Then let's insert 26, and let's insert 35, and then finally let's insert 77. Okay. Now let's say these are the numbers which are coming in. How would you do it in chaining? First of all, in chaining, what you will do? You will take 3. You will take 3 modulo 10, which is 3. So you will put 3 here. You will come to 5. You will do 5 modulo 10. It will be 5. You will put here. 7 modulo 10 is 7. You will put it here. 15 modulo 10 is 5. So you will come here and you will append it here. Right? In this way, you will build up the chain. So this is chaining. This is trivial, like simpler. Let's talk about open addressing. So in open addressing, how would you do this? My tablet keeps freezing for some reason. So now 3. First 3 comes in. You do a 3 modulo 10. You do f of 3. So let me just write down f of 3s for all of this. This is 3, 5, 7. F of 3 here is 5. This is 6. This is 6. This is 5, and this is 7, right? F of 77 is 77 modulo 10, which is 7. So now you have 3. You took its f. It came to be 3. What you do is you come to 3, and now you start the process of probing. So you keep looking for a place, an empty slot. So you first saw 3. You said, oh, this is empty. So let me insert it here. So the probing is finished. Now let's move on to 5. When you are inserting 5, you do f of 5. So you get 5. Now you come to the 5's location, f of 5, and you start the process of probing. So you first look at this index and you find it empty. So you put it. That's a very trivial probing that you have done, wherein you stopped or terminated in the first step itself. Now you have 7. So you do a 7 modulo 10. It comes out to 7. So you come here, and the probing is again trivial. You will put 7 here. Okay. Now let's do 15. So now you have 15. You will take 15 modulo 10. It will come to 5. So now you will come to index 5, which is this index. And now you will check. Now you will start the process of probing. So you look at 5 and you say, oh, 5 is already filled. So I cannot fill 15 here. So you will move on. You will move up, or you can move down depending on the probe, the type of probe that you are using. That's not important here. So you go up, let's say you see 4. Oh, 4 is empty. So let me put it here. So you will put 4 here. Now let's move to 6. You will do 6 modulo 10. You will get a 6. So you will come to 6. And 6 is already empty. So what you will do is now you will put 6. Let's change this. Let's make this 34 instead of 35. And let's make this is fine, 77. So now 6 is inserted. Now let's come to 34. 34 modulo 10 is 4. So now you will come to 4. And now you will see, oh, 4 is already full. So you will start the process of probing. Then you will come to 3. Oh, 3 is also full. So you will go to 2. Oh yeah, 2 is empty. So now you will insert 34 at 2. Then you will have 77. 77 modulo 10 will be 7. So you will come to 7. You will see, oh, 7 is full, 6 is full, 5 is full, 15 is full, 3 is full, 34 is full. You will insert it here. Had you gone here, then you would have come back here. You could have done a cycle. Like in a modulo fashion, round robin fashion, you could have probed. That's okay. So this is how you insert. So now you can see that an element, let's take 77. Its ideal location is 7, right? But its address is actually not 7. 77 is at 1. That's because of the technique that we have used, which is open addressing. So insertion is clear. Do you have any questions on insertion? How do you go about inserting items?
What happens if there are more than 10 data means?
So then you will have to resize the table. That is a limitation, yes. You will have to resize it and then make it again 20 and then start copy, insert those 10 items in that 20. So the problem, it is still solving a bigger problem, right? Because the range is not the bottleneck here, right? That was the bottleneck with a direct access table, which is not the case here. Insertion is clear to everyone? Others? So now let's talk about the process of deleting. So now after all these insertions, let's say that I want to delete. Let's say I want to delete 5 first. So let's say I want to delete 5 and then let's say I want to delete 77 and 3. And after deleting these, let's say I want to insert let's delete this first. So now let's delete, you are deleting 5. So you will take a 5 modulo 10. It will be 5. You will go to 5 and you will now start the search, the probe for finding 5. So you will find 5 here itself. So you can delete it. So now you will come to 77. You will go to 7. 77 modulo 10 is 7. So from there you will come back to 7. Now you will start the process of searching 77. So you will start probing. You will keep going up. 77, no. 77, no. 77. Now this is the place. Now see. 77, no. 77, no. 77, no. No, 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 no. Yes. So 77, yes. So now you delete it. Okay. 3. Go to 3. 3, yes. Delete it. Okay. Now let's say after this, you wanted to delete 35. How would you delete 35? You would start from 5. You will see that this is not 35, 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 this is not 35. So you will basically keep searching, right? When will you terminate?
When we find a vacant cell.
When you find a vacant cell. What do you, so when you find a vacant cell, Okay, so let's see. So somebody told me that when you are deleting or when you are searching, stop when you find a vacant cell. So let's come back to the problem of deleting 77. If you were using that technique, you will come here. 77 no, 77 no, vacant cell. So you will return not found. Right? Do you understand the problem? So how can you take care of this problem? So, is everyone getting the problem here? Intuitively, if even if not like in a very structured manner. So the question is, when will I stop the process of probing? So for insertion, I will stop till I find a vacant cell. I just told you that. For deletion, somebody just said that stop when you find a vacant cell. I just gave him an example wherein if you delete 77, you will stop even before you find 77, whereas 77 actually exists. You will start from here and you will come here and you will basically. So my question is, when will you stop the process of probing for any case, for either inserting, deleting or searching for that matter? Then we will travel till we get back at same position where we started. Yes, that is correct. That will be correct. But can you do better than this? This will take time, which is equal to order of size of the table. If the table is very large, what do you mean a vacant cell, Ankit? That's what I just told you, right? If you stop when you get a vacant cell, you will not have deleted 77. You would have started from here. You did not find 77. You did not find 77. You found a vacant cell because 5 has already been deleted, right? So you will stop here. You will not actually go ahead and delete 77, whereas 77 was actually present, right? So so does everyone see the problem? Two questions. Can you act for this? Do you understand the question that I'm asking, and do you see the problem with the most obvious solution to that problem, to the question? Just these two things. Let's not like go further. Do you understand this first? So let's think then. So then one very basic way of doing it is, you, as Karan said, you can keep probing till you reach the place where you started from, which is fine. Yes, that's obviously the best way. That means you have exhausted your search. But isn't this a linear search again? So didn't you like go back in time, go back 20 years again, and aren't you back to the same place where you started from? You said, I want to search efficiently, but then you are saying that I will keep searching for the entire size of the data structure, right? So you are again doing a linear search. So you have basically again gone back in time. Can you do better than this? If the table is too large, then this will have a lot of time complexity. Yeah, Shubham.
So we can stop when we find we find a value which has the same functional value, but it is not equal to the target.
What do you mean same functional value?
Like when we want to search for 77 and we did not find 77, but we found something like which gives modulo 7, then we can stop, because
you got a 7 modulo. You will always get a modulo 7 at the place, right? 77 modulo 10 is 7. You will stop this search at 7 itself. There might be in between also. You will have a 37 somewhere. If you inserted 7 and then 37 and then 77, then you are saying I will stop at 37 for deleting 77 also, right? Because how would you have inserted 7, 37, 77? You would have inserted 7 here, 37 somewhere here, and then 77 somewhere here. Somewhere after 37, 77 you would have inserted, because that's how probing is.
So here we can check like randomly, like we can do 2 times of that 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 element position.
No, That's okay. Random, you can just go to random places and search. That's okay. But when will you stop? The question is the stopping. It is not the probing algorithm. I am not concerned about how you are probing. You
Okay,
can
okay.
probe linearly. You can probe one after the other. You can probe randomly. You from 5 you can jump to 1, then you can come back to 3. It's okay. I am
So,
not really concerned with how you are probing. The question here is, when do you stop?
sir, when we delete element, maybe we could mark that cell as some number, let's say -2. So when we encounter a -2, we know that it has been deleted and we move forward. But for the first -1 which we get, which we know that, oh, like this is empty, so we can terminate then.
Yes. Yes, that will work. That is actually the bookish solution that is given in textbooks. You're right. So one way you could do it is just think about how 77 was inserted. So you started from 7 and you will keep going up till you find a vacant slot, right? So once you get a vacant slot, you will insert it. So what does that mean? That means that when 77 was inserted, everything from this index to that index was full. Correct? So what is the issue now with searching from deleting 77? You will always start from here, right? The issue is only when you come to an index wherein the element which you have deleted, right? Then the problem is that do you stop the search or not? So don't you think that if I keep separate markers for removed elements compared to vacant cells, then we can do this? So if you keep -2 as a marker to signify that this element was there, but it has been deleted, and you are keeping -1 to say that there hasn't been any activity on this cell till now. You have not inserted or deleted or done anything on this cell. So then you can keep going on till you either find an element or you find -2. And as soon as you find a -1, you can stop the search. किसी को समझ आया ये? I can go again.
Yes, sir. Understood.
Right? Do you see the problem is you have a 7 here, you inserted at this 77. So the only cells that will pose you a problem or hindrance in this searching is the elements which were present previously, but now you have deleted. Right? Because that's how you are, that's the algorithm how you are inserting. You are inserting to the first vacant cell. So everything between 7 and 77, between these two indices is full when you was full when you inserted 77. Now you could have deleted one or more elements in between, which is where the problem will lie. So my solution is, then when you are deleting, have another representer or a marker for that, right? Just have -2 so that you don't stop the search. So now you stop. So now let's say now you are basically searching for 87, let's say. So now you start from 7 and you know that if I reach a -1, then definitely 87 is not present. Why? Because had it been present, I would have inserted here. Worst case. That's how I would have probed, right? Starting from 7, I would have kept on going up till I encountered a -1, till I encountered a vacant cell, and I would have inserted it there. So you can stop the search when you get a -1. But insertion, you can insert at a -2 also. So it's not that you are occupying the cell. So now let's say you get a 67, you can keep going from 7 and you can insert 67 here at 5. That is fine. That does not affect, right? So you can insert at -2 or -1. When you delete it, you mark it -2. Initially, everything was marked -1. When you search till you reach a -1. If in the process you find 1, then you return true. Otherwise, you return false. So that is the entire picture. Is this entire picture clear to everyone, along with the problem, the solution? Others? Yeah. So this is how you can take care of this issue that is there. So again, in open addressing, so this entire technique is called open addressing. Now some more funda, not really important, but yes. So in open addressing, you can have different types of probing techniques. Here, what did we do? We were probing linearly, right? We started at an index and then we were going to the next smaller index, and then again coming back next smaller, and this is called linear probing. You are probing in a linear fashion. You are going one cell at a time. You could do quadratic probing. So what you are doing in a quadratic probing is you could do from 5, you are jumping 2 places, and then 4 places, then 16 places, then so square, let's say you are doing a square every time. So that is also another way you could probe. Correct? So that's not really very important, but that's basically what is probing, and various ways you can probe. There is a entire like theory on this also, but that's not very like relevant to us. If you getting a feel of this is important. So in the complexity of insertion, deletion, and searching is the same as that of what was that? Chaining. The complexity is the same. Why? Because you are basically, I mean, there's a theory in this that inserting, basically you will keep on going up. So in best case, or if you have a function that is well behaved, then all these operations are order 1 on average. So let's do that in a fresh page. So now let's talk about the complexities. So I just told you hash tables. I told you 2 possible ways you can implement hash tables. You can implement them using chaining, and you can implement them using open addressing. And let's talk about the complexity. So on average, hash tables, irrespective of the implementation, give you order 1 complexity for all the 3 operations: insert, delete, and search. But worst case, if the chain becomes linear, similarly in open addressing, if you have inserted all the elements, then in worst case, the searching could go up to order n. So that's basically the complexity. But in average case, it is order 1. And in most of the cases, we use functions which are well behaved. So it gives us order 1. This is the complexity. And that, ladies and gentlemen, brings us to an end on the theory of hashing and hash tables. We will now dive into applications, which is where we will look at real code. But I will take up questions on the theory if you have anything. Is everyone alive, awake? Not slept off? Do you need a break before we start applications? We can break for 10 minutes. You can do some stretching if you want, and then we can come back. We will come to USP is basically unique selling point. We will come to that. So yeah, let's proceed then. So Karan, I just told you this, you can just take it from me as it is, that if the function is well behaved, that means it distributes the elements uniformly, then the complexity is on average is order 1. It is not dependent on the n. There is a theory, mathematical proof of this, which is not really important for us. Okay, but yeah, this is something that you can take it from me. but the intuition is clear, right? If you distribute it uniformly, then every chain will have a constant number of elements. And because you will have, so, right? So let's say you had a size input of range n and your hash table was of size n by 2. So then on average, every chain has 2 elements. So that is basically constant. So the time complexity is constant. Most cases, if it is worst case, you understand, right? When the chain becomes linear at a particular cell, then it can go up to order n. That's basically the intuition which you can take it, and that should be enough. The mathematical theory is not really important, but remember the complexities basically.
Do we have any drawbacks of using hash tables?
The drawback is worst case, it does not give you any efficiency. Like if you choose a bad function,
okay,
then you are going back to the same, like now you have linear complexity, so you have not done anything. So because the major drawback is everything is average, on average. This worst case, it can still go up to, we will see data structures wherein we get average, worst case, everything as order log n. So no matter how skewed the data is, no matter what may, it will always be log n. Whereas hash tables, depending on the data and the hash function, might perform as bad as order n, right? So then there you would prefer this, right? Because this basically boasts of the fact that no matter what, come what may, I will give you log n complexity.
okay, sir.
Okay, so let's now move on to applications, which is the real stuff. So this is hash tables, right? So now let's see, first things first, let's see in C++, in the standard template library, how are these implemented? So you basically, libraries, what purpose do libraries serve? Libraries serve the purpose that they give you predefined functions and predefined data structures that you can use. So C++ STL gives you hash tables. You can use them. So you can use, and they give you an interface to access hash tables, insert, delete, search in an hash table, which is what we will be looking at. So so typically you define a hash table using an unordered map. This is the keyword that you use, unordered _ map. And then in the template argument, you specify the data type of the hash table. So if you want to store integers, you specify int here. And then you can declare a variable. Let's say this is table. So this basically declares an empty hash table. Or in fact, it defines an empty hash table if you are very precise about things. Now, once you have an hash table, it will be int comma int. So basically, if you remember, there were two things in any hash table, right? That we looked at. You had, so for every x, you were basically having, what were you doing? You were going to f of x, and then you were putting in some value here, right? Which could be a counter, which could be a key, or anything you could put here. So this x is actually called the key, and what you put in this cell is called a value. So you could, maybe if you are keeping frequencies of every number, you could keep a counter here, which you increment as you get x's. If you are just interested in storing that value itself, then you could just store the key itself, right? So hash tables in C++ give you a way to specify both the data types of both. The data type of the element that is coming in, which is the first argument of this template, and the data type of this cell, this location where you put value, which is, you can take an integer and then you can define a table. Okay. This is a comma, a very bad comma. Once you have declared this hash table, how would you insert? You can do a table dot insert with the key value. So let's say you want to insert 3 and you want to put a value of 5 for that 3. So what you will do, you can do a table dot insert 3 comma 5. What it does underneath is it takes the key, it finds f of 3, it goes to that location and then it puts 5 there. So this tuple that you specify, you cannot specify in its raw form. You will have to make a pair. So you can do a make underscore pair 3 comma 5. So this will give you a pair and then you can do a table dot insert with that pair. We will come to that, but yeah, that's basically the syntax. If you want to delete, you could just do table dot delete and the key. So you want to delete 3, you can simply go do table dot delete 3. So it will do go to f of 3 and then it will do open addressing or changing depending on the implementation and find the exact value, the place where 3 is, and then it will delete the value 5 also, 5 from there. So this is table dot delete. You could search, which is table dot find. Table dot find with a key. So it will give you it will search. Okay. So search, when you do a search, it will return, once you do a table dot find k, it will return an iterator or a pointer. You can just assume it's a pointer. So it will return a pointer to k. So what it will do is it will do f of k. It will go to that particular location. It will do probing. Let's say it was doing probing. Once it finds the value of b, it will return a pointer to that. So now, once you have that pointer, let's say this pointer is IT, then you could do IT arrow first. This will give you 3, the key. And you could do IT arrow second, which will give you the value, which is 5 here. These are just interfaces that C++ defines. So once the pointer is there, with that pointer, you could do this. You can change it. So if you do IT arrow second is 7. So what you have done is you have changed the value of 5 to 7 now.
Sir, if we need to access the key or the element value without using iterator, then we will use the dot operator, right?
So star IT dot. So because this is a pointer, you want to dereference it and then do a dot. If you are really you want to go into the specifics, okay. So basically, this IT points to an object which contains the key and the value. It contains a pair, key comma value. So for any pair, so for this object, let's say this is X, you could obtain the key, the first using X dot first, and you could obtain the value using X dot second. Now you don't have X, right? You have a pointer to X. So how would you access K? You will do star IT dot first, right? Star IT will take you to this location, dereference it, then you will do dot first. So this is IT arrow first. Just
Sir,
pointer
actually
arithmetic.
Hello. There is another way to insert into the unordered map, right? Like as we do in the array also, we can use table of, square brackets.
Yes, we will come to that. I will come to that.
Okay.
Yeah, so these are the ways you can insert. Another way you could insert is you can simply do table in square brackets, similar to what you do in arrays. You could do a key, pass in the key, and you can do an equal to v. So this will assign at, so what this is basically equivalent to table dot insert kv. You could do this. This is also one way to insert. Okay, so this is the interface that C++ provides for a hash table. Any questions on this? For beginners, for people who has never had any kind of exposure to this? Yes, so unordered, we will come to that. Vidyut. Let's take this question tomorrow or day after tomorrow. You will understand why is it called unordered. Yeah, Karan, I can explain K and V. So K is the key, right? So remember in a hash table, what you had two elements, right? You had a table, you had a data item that was coming in. What you used to do was, you used to do an f of x, and that would be the location where you go. And then in that location, you can put something, right? You can put x, you can put 1, you can put -2, you can put anything, right? So what you put in this location is called the value. And the data item that is coming in is called the key. Is this clear? F of x is the index where you go to in the table, right? F of x is not the value. So you have things. See, this table is, let's say 0, 1, 2, 3. Let's say 4 size. Now you have 9 which is coming in. Let's say f of x is x modulo 4. So f of 9, so 9 is the key here. So f of 9 is the index where you go. So f of 9 is 9 modulo 4, which is 1. So f of 9 is 1. So you go to 1. Now what do you put here? You can put 9 also. You can put some other value. It just gives you the freedom. So that which you put is the value here. You can put 9. That's the most trivial way of, you can just put the data item itself. If, or let's say you had a big object, a user defined object. Let's say you had a person's object wherein you had the name of the person, the address of the person, the nickname of the person, the father's name, mother's name, all that. And you had a unique identifier for that person, which was the name, let's say. So then you could use that name to index into the table and store the entire person's attributes here. Right? So that is also one way you could look at it. Do you want me to talk more about key values? If k, yes, that's a good question. So if k is not present, it will give you a pointer to table dot. So it will give you table dot end, which is basically a pointer to the pointer one more than the last element of the table. So basically it just tells you that I did not find it. So I am returning after. So just think about when you do a search, what happens? You keep searching. Once you reach the end, you advance one more step and then you realize, oh, I have reached the end. So then you return. Similarly, this is what table.find does. It will go reach the end. It will advance one more and say, oh, I have not been able to find. Now I should return. So it will now return and it will return you the index, the pointer to that element, which is one more than the last element. One more in that address, in terms of address. More questions? No, it is defined. So if you have, so what is it hashing? It is hashing the key, right? So if you have a key which it understands, so let's say you have an integer, you have a double, you have a string, any primitive data type you have as the key, then it understands that. So the hash function, it has predefined hash function for them. But if you have a custom data type, let's say you have an imaginary number as the key, then you will have to specify your hash function. Yes, we can. So that's basically the third argument. There is another argument which you can pass apart from the key value, which is the function name. So you can basically encapsulate, similar to what you do in hashing, similar to what you do in sorting. You encapsulate a function in an object, right? In a structure object, you overload the operator and you pass that structure here. Similarly, you can encapsulate that function in an object, which is called a function object or a functor, and you can pass it here. That is like just syntax details. You can look it up. That's not like I wouldn't put so much emphasis on that. Where will you specify it? But yes, it's good to know that you have to specify your hash function if you want it to be, if you want the hashing to be done on a user defined data type, which the library does not understand. Syntax you can always look up where to specify and how to specify it, like how do you overload the function. That is. So are others getting these questions? These are good questions, by the way. These are not very trivial questions. You can ask me follow-up questions on questions that they are asking. Any more questions on this? All good? Can I have acknowledgements so that I can move on? Yeah. So this is how you define it in C++. Now let's start with some applications of hashing. Let's do this question. Do you need the question number also? Or do you see the link? Do you need the number also? I think some of you might need it because Zoom has updated, so it is no longer a link. But you can copy paste this link, right? Have you read this question? Yeah, okay. Let's discuss. It's fine. It's not. These are not very easy questions. So let's see. So now you understand the data structure, right? So what is the USP of this data structure? What is USP? USP in entrepreneurship world is unique selling point. So every product has a unique selling point because of which it sells in the market, right? Because of which users buy it, and that's basically called the USP of a product. So for instance, you might have the USP of a Dove soap is very different compared to the USP of a Pear soap, right? So they have like their own USPs. Head and Shoulders USP is that it stops dandruff. Might be some others shampoos USP might be that it makes your hair silky. So every product has a USP, a unique selling point. This is not product, this is point. So this data structure also has a USP because of which people use it, which is basically efficient searching, right? You are able to search, insert and delete in average order one time in a dynamic fashion. So that's the USP of this particular data structure. So whatever problems that we will look at typically will have this pattern that you have to search for something, and you have to, so there will be times when you will have to insert items, and then you will have to look up these items, then insert again, delete, look up. So this process you will have to do in those problems, and that's when you should think about hash tables. If you have such a problem at hand, then you should think about hash table. So this particular question is basically telling you that you have strings, you have eat, you have tea, let's say you have eat, you have mat, you have time. So you have to group the anagrams together. Anagrams are basically strings which have the same characters, but the order might be different. So for instance, eat and tea are anagrams. Similarly, AET and EAT are also anagrams. Correct? So you have to group the anagrams together. So you have to put EAT, TEA and AET together. You have to put MAT and TAM together. This is one anagram, one set of anagrams. This is one set of anagrams. That's what you have to do. So let's think about the brute force way of doing it. What would you do? How would you do it in a brute force manner?
We take each element from the list and we sort it to each other if they are equal.
You sort the list or you sort the individual strings?
Individual strings, not the list, individual strings. Or we can take each element value and the other element value separate it from.
Yeah, just think about the brute force way of doing it. How would you have done in a brute force manner? So the first string you would have taken you would have said that, okay, this will be in one of the groups, right? Then you take TEA, and whatever groups you have already populated, you will check whether TEA belongs to any of these groups or not. How will you check? You can simply count all the characters, right? So you can count how many A's are there, and you can count the number of A's of any element of this group, number of E's and number of T's, and if all of them are equal, then you know that this basically belongs to that group. So then you can put it there, and then you can move on. Otherwise, if you don't find any group, you create another group for it, right? This is the brute force way of doing it. You could count each of the characters, or what you could do is you could sort this. So if you sort this string, what happens is all the alphabets become sorted. Now, so the best part about anagrams is that if you take any two strings which are anagrams, and if you sort them, both of them will be identical, right? Because the characters are the same. It's just the order is different. So what you do by sorting is that you specify an implicit ordering, which is basically AET, and then every string that you take will basically, after sorting, will become AET, right? So one way you could do it is that for the entire group, you have one representative element which is sorted, and as and when a new element comes in, you sort it and you check if that element is the same as this. If it is the same, then you know it belongs to this group, and then you can insert that element. Otherwise, you can create a new group, right? This is the brute force way of doing it. Is the brute force clear to everyone? Or should I explain further any point? Karan, is the brute force clear to you? Yeah, now let's think about, if this is the brute force way of doing it, what are you doing basically? So now let's talk about each of these individual things. You are maintaining groups, right? So how could you maintain groups? You could maintain them in a 2D vector, right? So in a 2D vector, you could have small 1D vectors, and each of these 1D vectors is a group. G1, this is a group G2. So that problem is solved. So then basically what you do is you can iterate through every vector. Once you have an element, you can iterate through every vector, take up one element, sort it. So once you sort it, you will get a representation, right? So take up an element, sort it, and then sort the current element also, and check if they are equal. If it is equal, you can append. Otherwise, you can move on to the next vector. Right? This is what you can keep doing. So what is if I represent a group in this fashion in a 2D vector, what is the total time complexity of this brute force solution? So what are you doing? For every string, what are you doing? You are going through all the elements which have not yet been, which have already been populated in groups. So worst case, you would have to traverse n groups, where n is the size of the array, correct? So for every element, worst case, you could traverse n groups. So for every element, you are doing n operations when you are traversing these n groups. Now for each of these groups, what are you doing? You are sorting and then comparing. So sorting, if the string size is of length k, sorting is k log k, right? And then you are comparing. Comparing is another k. So the total complexity would be n into k log k. K log k plus k is basically k log k. Right? So the total time complexity of this brute force approach is n into k into log k. Is this clear? The complexity? Others? You are seeing the algorithm, right? Just the brute force. I will take you systematically how we are arriving the optimal solution. So if this is the brute force, now let's see where can we optimize. See, this part is more or less okay. Can you optimize this? Tell me this first. Can you optimize sorting? You can optimize sorting by using counting sort here, because you know that the strings are from range A to Z or A to Z, right? Do you know counting sort? I guess you know counting sort, right? So don't you think you can optimize the sorting using counting sort, and then the sorting becomes K? Not even K. Yeah, it becomes K. It becomes K plus 26, which is K. Correct? So the sorting you can optimize. So this becomes K. Can you optimize this N? What is this N? This N is that for a particular element, you are traversing this 2D array. So immediately you should think about the choice of this structure that you made. Was it a wise structure? What is happening in this structure? You are inserting every time. You are searching every time. Right? So immediately you should question the choice of this structure. Why did you choose a 2D array? Can you do better? Now this is something that you should answer and I will not answer. What structure can you use which would be better than this? Is everyone on the same page with me? So far? Like how am I incrementally approaching the question?
Could you repeat the question again?
Can I repeat the question? So the question is telling that you have to group all the anagrams together. So anagrams are basically strings with the same characters. It's just that the order of the characters may be different. So you have to put all the anagrams in together. So these are anagrams. You will put them together in one group. MAT and TAM is an anagram. So both are anagrams. So you will put them together in one group. So the structure here, do you see that you are inserting every time and you are deleting every time? Right? Not deleting, you are searching every time and you are inserting every time. Do you see this? First of all, can I have acknowledgements if you see this? So if this is, and you know that we just talked about a data structure which enables you to do this efficiently. So can you use that instead of an array? You are basically going back in time if you are using an array here, because you are.
Sir, if we have same frequency of characters, we can use same hash function for those.
I have not yet introduced hash functions like here. So just bear with me. Let me finish this. So now think about, so now you are saying that, okay, let's use hash tables. So what kind of hash table can you use? So remember, the first thing that will come to my mind now is the key. So now I am on my way or en route to designing a hash table, right? So now I am en route to designing a hash table. So I have to decide my key value, right? So what could be a good choice for the key? If you remember, in every 1D array, you had a representative element, right? You did not actually explicitly store that representative element, but what you were doing was that you were picking up the first element and you were sorting it. and that was giving you the representative element. So what is that representative element? That is basically nothing but an identifier for the entire group, right? So can you have that element as the representative element, so that when you encounter a new item, let's say you encounter EAT, you can sort it to get the representative element, and then you can use the hash table. This then becomes the key, and then you can use it to index into the hash table. So that way you are able to look into a group dynamically or search for a particular group in order one time, right? Here we were searching for a group through a linear pass. We were going one after the other, looking, checking against every group and seeing whether my current element fits into that group or not. What I have done now, if I use the sorted element or the sorted string as the key, is that now I am able to find my group if it exists. If it does not exist, then obviously I will insert. But if it exists, I am able to find it in order one time, instead of doing a linear pass and finding it in order n time. Does this make sense? What about others? Karan, is this making sense at some level? Ayush, Dominic, Hemant, Jadav, Nirav, Radhika, Sai. So then my design of data structure, immediately I tell is that the key is the representative element. Now let's come to the value. So the value is a group, right? So what is a group now? A group is nothing but a set of strings, right? So can I have an array as the value? This is nothing but all the elements, all the elements of that group. So all the anagrams grouped together, right? I am just transitioning. I have just told you that from this 2D array, how am I going about and designing this hash table? What all did I look for and how I went about this? So a group, I told that I need to identify the group so that I am able to index into it immediately and get access to that group in one time. So I said that why not use that representative element as the key. And then I said that once I have done that, I need to store that item in that group, right? So how is a group represented? A group is nothing but all the strings. So can I store all these strings using a vector? So that once I get any element, let's say EAT, what I will do is I will sort it. So I will get EAT and I will use that to index into the hash table, and I can append EAT at the end of this. So this is my thought process. So what is the total algorithm then? The total algorithm is that I have an unordered map, which is a hash table, where the key is the string, the representative element, and the value is the vector, is a vector of strings. Now what I do is I go through, so now I have a list of strings that I am given S1, S2, S3. Now I go through every element in this list L, and what I do is I sort SI, and then I can find SI here. So if I find SI, and if I found it, then what I will do is I can simply insert. So M of SI will give me the value, right? So I can just insert. So M of SI is an array. I can do M of SI dot pushback SI. Not SI, the unsorted version of SI. Let's say SUI. And if it is not found, then what I can do is I can create an array here. I mean, you can, so basically it will still be the same. You have an empty array, so you will push back here also. It's just that you will have an empty array to start with. And once you are done with this, basically you will have a hash table wherein for every key you will have a set of anagrams. And now what you can do is from here you can return the result array, which is the 2D array, by going through each of the elements of the hash table and creating a vector for each of them. Right? So you will create a vector for this and you will put these elements. So this entire process of converting the output from a hash table to what the type of the output that they want is again order n. Actually it is, you are going through it and you are pushing it. So what is the complexity of this? So is this algorithm clear first of all? Can I have acknowledgements if it is clear?
Sir, in the string called key, what we are actually giving it, like in the example we had cat or like that. So what we are passing there?
Where? Come again?
In the key called here you wrote string, right?
Yeah.
So in that, what we are actually passing then?
Key is the sorted. We sort the string and we pass the sorted string.
Okay, so it contains like if we have an example as cat, so does it have cat or tag or
It has
AT?
ACT. You are
Why only
sorting
ACT?
because that is the unique representation for that group. You can identify that group using that. Every element in that group, for that it will be ACT, right?
Okay, so is it like alphabetically?
It is sorting. When you sort a string, it will be alphabetically, right?
Okay.
So let's see the code. Things will become clearer. And then so let me. So let's see. So what is the first thing you will do? Your map. So you have now what I will do is I will level up. I will basically populate the result also on the fly. So let's say this was the map. Do you want to try it on your own or should I code it? I will code this, I think. Just give. Yeah, I will code it. I will code it. Just a second. I'm just replying to my manager. I was scheduled to have a one-on-one with him at 9 today. But seems like he was preoccupied with something. So he postponed it to 10:30. But now I have mailed him to postpone it further to 11 or 11:30. And we will start from, like, I will have it at 11 or 11:30 with him. So it's a weekly one-on-one that we have. So he's in the US. Just a second. Okay, it's from 11. Okay, let's code now. He replied. It's fine. Okay, so what did I do? I am creating a map, a vector, a hash table. Let's call it table, which has an integer and a vector. Now, I will have a result array, which is a vector of vectors. This is the result array. Okay, I have not done anything else. Let me go through the elements of the list. So I will go through the elements of the list. N is strs.size. So I go through each element. Now each element is a string. So what I will do is I will sort this, right? So let me have a temporary string, sorted str, let's call it. So I will just copy it. This is strs of I, right? Now I can sort this. Let's just use the sort function of STL. You can basically sort using your own counting sort function also, but that's not the point that I want to show through this question. So let's just use the sorting function. So now I have sorted it. So now this sorted str is the representation, right? So now I will try to look it up. So I will see if table.find of this sorted str. So if it is equals to table.end, so basically what that means is that the element was not found. Okay. So if this is the case that the element is not found, then I will do something. Else the element is found, I will do something. Let's think about what all we will be doing. First, let's come to the case when you found that. So a group already exists. So what you will do is you will go to that value. So table of sorted str will basically take you to that value. So that value is a vector. So table in square bracket, the key will give you the value. So the value here is a vector. So in that vector, first of all, this is string, and this is also string. So in that vector now you will push back. What will you push back? You will push back this string. Correct? Otherwise, what will you do? Otherwise also you will push back. It's an empty vector, so you will push back. So in both the cases you are pushing back. So you can basically remove this. Okay, so this is basically what you have done. Now you have the table populated. So this was phase 1. Now phase 2 is basically convert the table to a 2D array. So that's pretty straightforward. What will you do? First, let's define an iterator to this pointer to this table. So a pointer to this table is basically you just copy paste this entire thing, double colon, the keyword iterator. So this gives you the pointer to a structure of this type. Okay, so this is the type, double colon, and then the keyword iterator. This gives you the pointer to this structure. So you can define an iterator. Let's call it IT1. So for traversing this table, basically you can go as IT1 is table.begin. So table.begin will give you the iterator to the first element in the table. And then you can just loop like you would normally loop. So you will keep going till you encounter table.end, and you will do a plus plus every time. So you are moving to the next element. So now IT1 is pointing to a particular table, to a particular element index in that table. What will you do with that? You will basically populate the result from here. How will you populate the result? First, you will push back an empty vector because this is a group. So you will push back an empty vector.
Directly push back the it dot second to the result vector, right?
हाँ you वो भी कर सकते हो, वो simple हो जाएगा. Yeah, because it's already a vector. You're right. You can simply push back it arrow second. It arrow second is the value, which is a vector. So you are pushing back the entire vector in this result, and then you can return result. You can do both of them in one pass also, but that's okay. That's not the point of the question. I will have to log in. This DSP patches, right?
So I didn't understand that IT arrow push second part. Could you explain that?
Yeah, I will. First, let me check whether it is correct or not. Okay. Yeah, Darshan, what is the question? Hello.
Sir?
Yeah, you had a question, right?
IT arrow second, that line, press dot push back IT1 arrow
This one,
second.
right? Yes. So IT1 is an iterator which points to an element of this type. So an element of this type has two things, the key and the value. So the key you can access using IT arrow first. That will give you the key. IT arrow second will give you the value. The value here is a vector. It's an array of strings. This result is a 2D vector. So every element of this vector is a vector. So what you could do is, I am in this. So the one way of viewing this is basically it's a 1D array of 1D arrays, right? So with that view, what I'm doing is I am pushing back IT1 arrow second. This is another entire vector, right? So when I'm pushed back a vector in a 2D vector, basically I am, right? Do you get this, no?
Yes, I got it.
Yeah. Others? Does this make sense? Clear? No problems with the syntax, no problems with the logic, no problems with the approach, how I approached it. See, you will always be able to understand a solution when I give you the solution. There is no rocket science in that. But the point of taking these lectures is you should be able to see how I approach it and how I came to the solution. What was my thought process behind it? And that is what I tried to explain through this question. How in my head, I justified or I convinced myself that I would need a hash table, and I worked out the details of the hash table and how I used it to solve the question. So those things are more important than understanding the actual solution. You will understand the actual solution, I know. but that's not the point. The point is to understand the approach. Second is the value. First is the key. It's a keyword. Does that answer your question, Sakshi? So if this is how you do it, what is the, let's come back to this question. Let's talk about the complexities. So what is the complexity of the brute force solution? So let's come back to the brute force solution. What was the brute force solution doing? The brute force solution was for every element going through all the groups. So going through a group, all the groups might take n time, and it was first sorting it. So sorting will take k log k. Once it has sorted it, it was going through. So for every element, what it was doing, it was sorting the first element, which is k log k, sorting that element, then going through every group, and in every group, what it was doing was it was going through each of these elements, taking the first element, sorting it, checking if they are equal or not. So that takes k time. So this is one pass. Then in a loop, you are doing a for. So in the loop, basically you take n time, and for in every iteration, you take an element, you sort it, and you compare it with this. So this is n into k log k. And once you find it, you push it here. So pushing is another k, right? Because it is a string and not an integer. So this is the total complexity of the brute force solution. What is the complexity of the optimized solution? In that optimized solution, for every element, you are accessing the group in O one time. Once you have accessed the group, you are pushing that element. So you are sorting it, but that is a one-time operation, right? And then you are accessing the group in order 1. Then you are pushing it in the vector, which is order k. One second. So for every element, you are doing k. And this you are doing for n elements. So this entire thing you were doing for one element, right? So this you will do for n elements. So you will have another n. Am I right? What is the complexity? Did I mess up the complexity of the brute force solution? So my question is, just tell me the complexities of the brute force and the optimal solution. Like that's the question. Precisely, like exactly what will be the complexity. Can anyone tell me? Did you get confused? So think about every element. What are you doing for every element in the brute force? You are going through all the groups. So if you are at an position I, how many elements have you already seen? You have seen I elements, right? So if you have seen I elements, at max there could be I groups, right? So you might take I time to iterate through all the groups. Once you find a group, you will sort an element using k log k, and then you will push back. So that will be a total of k log k plus k, right? And this you will do for all the i's, 0 to n minus 1. This is the complexity of the brute force solution, which is basically nothing but 1 to n minus 1 is order n square, right? So this is order n square k log k. roughly. Correct? Is this complexity clear of brute force, or should I explain? Can I have answers? Are you guys there? Clear? Yeah. So now in the optimal solution, what are you doing? For every element, you are simply finding that group. So this time is not there, right? You are not iterating through I groups. So that is one order one time. And then basically you are doing the same thing. You are pushing back. So pushing back will take k time. And this you are doing for I equals 0 to n minus 1. So this is n into k. N into k, and then you have one sorting that you do for every element. So n into k plus k log k. That is there obviously. So it is roughly order n into k. So this is basically, you see the improvement in the solution just because you used a hash table. So this is for the phase 1, right? Phase 2 is also nk, right? Because phase 2 you are just iterating through all the elements of the table. So there will be at most n elements, and you are pushing back elements in the 2D vector. So that takes k time. So for every element you take a k time. So the total of nk time in phase 2 also. Phase 2 is basically once you are populating the result from the table. So the total time is order nk for this. Shall we move on?
Sir, once explain the code by the example there.
We sort every element. So sorting part. No, we sort every element. So it should be k log k for that element, and then it will be k for the push. Yes, you are right. So it will be n k log k. It will be n into k is for pushing, and this is for sorting. So n into k log k, and here this is n into k. So this total is n into k log k. Yeah, Andit, you're right. Any more questions?
Sir,
Jadav, you were saying something?
Explain the code by the example there. I didn't got it clearly.
Okay, so you get eat, you iterate through all the elements, you get eat. What is the sorted version of eat? AET. So you sort it. So sorted str will now contain AET. Then you do table of AET dot pushback. So in for AET as the key, you will push back EAT. Okay. So now basically you have this picture. AET, EAT. Okay. Now let's go back. The second TEA you will get. So you will sort that. You will get AET again when you sort it. So table of AET, which will be this, and you will push back here TEA. Okay. Then you come to TAN. So you will sort TAN, you will get ANT, and you will push back ANT. So you will get ANT arrow arrow TAN. This line is giving me that. Then I come to ATE, sort it, it gives AET, then you push back here, so you get ATE. NAT, you sort it, it becomes ANT, then you push back here. BAT, you sort it, it becomes ABT, so you push back, so you create another 1D array for this BAT. So this is the table after the iteration for this input. And then finally, you will go through each. So IT1 now points to this. So IT1 arrow second will be this entire vector. So you will push this entire vector in as the output. Then in the second pass, you will, now when you do IT1 plus plus, you will come here. So IT1 arrow second is this entire thing. So now you will do push back. So you will push this entire vector. And then you will come here, it will point to this, and you will push back again. So you will push back this vector. And this entire vector basically you will return.
Got it.
Yeah.
Sir, what is that you said like iterator pointing to struct thing here?
So you have a pointer to a table, right?
Yes, sir.
So I just gave you the syntax how to define a pointer to a, so a pointer to this table you are finding, right?
Yes, sir.
Pointer to this. So I just gave pointer to an element of this table you want to declare. So the syntax is that you declare the table, which is as it is, I copied it from here. Then you use 2 colons and then you use a keyword iterator and then you specify a name. So this entire thing is, so now IT1 is capable of pointing to any element in this table. So I first begin by making it point to the first element in the table, which I can get through table.begin.
Okay, sir.
Clear to everyone? Everything is fine? Shall we move on? Okay. So let me give you some questions on hash tables. So give them some thought, and we will continue our discussion with hash tables.